So welcome back, everybody. Before we begin with the continuation of yesterday's lecture, which was about notations and introduction to some of the basic formalism, I just wanted to remind you of some of the practicalities. Is the in the back? Can you hear well? I tend to lower my voice when after some time, actually, and then I'm not aware of it. So the this is the official website of the university, and when you click on, for instance, the schedule, you can actually subscribe to the schedule here. And what I typically will do then, you will find a link after we have uploaded the lecture, and there will be a video of the lecture. You can always revisit it. For those of you who may not be able to be here, you can always be on Zoom. So you have the Zoom link, and you also got an email with the Zoom link. If you go back here, you will see in the messages here, you will find also the Zoom link. And this is the one we're going to use for the rest of the semester. So in case something happens and you have to stay home, you're waiting for a plumber or electrician, which never come on time, then you can always follow via Zoom. And I will put messages here, but you will also get an email. And today, we're not going to have exercises because yesterday was just an introduction and with definition of formalism and so on. But from 8 to 10 on Fridays, we will go through exercises. Or next week, you will get a set of exercises. And you will get a regular email every weekend, roughly, beginning of the week, with reading suggestions and what we are going to cover. So everything should be hopefully pretty clear. So, yeah? Yeah.
The exercises are given on Thursday, and then we bring...
No, you will have the exercises when the week begins, and then you can always look at things in peace. And then when we meet on Friday, this is actually an interactive, so this is going to be part of the active learning, where we are going to work with exercises. And sometimes we may use the whole Friday on exercises, and especially when you're dealing with a midterm, then we will probably dedicate more time to discussing the midterms. Okay, you will find this information here, as you probably noticed, and if you go into the fall 2022, you will also find the link to the GitHub address, and the GitHub address is this one. And if you go into different folders, like in this doc folder here, you will find different textbooks which we have mentioned. And I'm going to give you the reading assignments from these textbooks. And the one by Szabo and Östlund is the one I'm roughly following now the first 2 to 3 weeks. So you can peep into the chapters 1 and 2 there. And that gives you also a reminder of linear algebra. Because again, linear algebra pops up everywhere. So we can't do without it. We would feel totally handicapped if we didn't use linear algebra. And then the material which I'm covering typically, like this week, I'm going through the slides here. I'm going to reorganize this, and you will also find everything as a Jupyter book. But that will be ready after the weekend. And you will find later, you will find the projects. I normally put in the handwritten notes here. So after every lecture, the notes I write on the whiteboard, they will be put in there, so you can always revisit them and see if there is something which is missing or whether there are typos and so on and so on. So this was just a quick reminder, and the material which I'm covering this week is actually given by these slides here. So it's an introduction to the course, linear algebra, but I'm going to dive quickly into the whiteboard so that we can remind ourselves of some of the technicalities here. And the textbooks which I normally follow is Shavit and Bartlett, Szabo and Östlund, and Nagel and Roland. And you have access to the PDF files. So some of these are out of print, but other ones, for those which are out of print, you can actually just use the PDF file we provide you with. Okay, so I'm going to switch to the whiteboard if it's okay, because I wanted to go through some of the formalism and notations which we're going to use here. Now, feel free to ask questions if things are unclear, something you want to ask about. I wanted to remind you also to think of possible times for the oral examination, because that's going to take place sometimes in December, and we just have to find a date which fits everybody. Okay, so let me switch to the whiteboard and quickly remind you of where we ended yesterday, and then we are going to move on. So what we did yesterday was to bring up several basic definitions of notation which we will use throughout the course. So we will typically use the bracket notation. Sometimes this notation will be pretty compact, but the compact expression will most likely be linked with a given context. So in case you have an X here, this could represent a many particle state, but it could also represent a single particle state. So depending on the context, it should be clear what that specific symbol means during the lectures here. So we were just going through things like this, definitions of orthonormal basis. An outer product is a quantity which we are going to use again and again, especially when we define these projection operators. These are important quantities because they're going to split our Hilbert space in different parts, and these will allow us to define an effective Hilbert space. And as I said yesterday, all of physics, I mean, irrespective of whether you do quantum physics or whether you do classical physics, astrophysics, is always about finding the relevant effective degrees of freedom. So sometimes you have a formal mathematical transformation from the fundamental degrees of freedom to effective degrees of freedom, but in most cases you do not have that. So typically when you go from quantum mechanical formulation to a classical mapping of an effective classical potential, which you can use in molecular dynamics calculations, there is no rigid and formal mathematical transformation from one type of effective degrees of freedom to another type of effective degrees of freedom. In other cases, you do have that. In physics, we have something which is called renormalization group theory, and that gives you a formal mathematical prescription for transforming from one set of degrees of freedom to another set of degrees of freedom. So the whole problem, as we also ended yesterday, is that with an infinite basis in our Hilbert space, we end up with infinitely many degrees of freedom, and we are not able to tackle that. Unless you can solve the continuous Schrödinger equation analytically, you will always discretize it. When you discretize equations and you have an infinite basis, it means simply that you have to make truncations. So that's the kind of overarching philosophy. And basically all the ways we deal with physical phenomena, whether you're doing geoscience, whether you're doing astrophysics, is always about finding an effective representation. And then clearly you have to decide whether this effective representation is a rigorous one or whether this is just an approximation you make because you think life looks like that. Yeah.
Yesterday you said that this truncation error, we couldn't assess how big the error would be. Is this a quantum reason?
No.
Why is that?
No. So
because usually you can, right? When you make
it depends. It depends. You have like with a harmonic oscillator basis, you can actually make explicit proofs on what kind of quantities are left out when you make the truncation. But with other basis sets, you may not be able to do that. So in principle, you should be able to derive an error estimate. So with like the harmonic oscillator basis, it's actually possible to do that. And one of my former students, who's actually the supervisor of Henrik here, he actually did that on his thesis. So, and that was within the framework of a harmonic oscillator basis and Coulomb type of interactions. So just let me quickly remind you of some of these things. So we went through the single particle state functions. We will often use a compact notation like the one which you see here. But in other occasions, we're actually going to deal with all the degrees of freedom. So it's pretty common, especially when you use second quantization. This is actually a mapping to another space, but where you leave out the coordinate degree, the spatial degrees of freedom. And that means that the spatial degrees of freedom, they will be incorporated into expectation values, which you will just read from a table when you need specifically matrix elements when you're solving quantum mechanical many-body problems. So these matrix elements are actually represented by integrals, and we are going to define these today. So that's one of the next items which we need to set up before we can actually move on to use such a more compact notation. And you will see that when we deal with all the explicit degrees of freedom, that when you move beyond some few particles, the notation and the calculations become clumsy. And then you're looking after a more efficient formalism. And second quantization provides you with that. So that's one of the main motivations. So because you wouldn't like to carry with you all these kind of symbols. It's easy to don't see the wood anymore for the trees, unfortunately. So, but today we're actually going to spell out things in terms of the all the coordinates which we have. So this will be typically spin degrees of freedom and the spatial degrees of freedom. Then what we did yesterday was also to define tensor products, which play a very important role. This is something which, if you have time, you could just look this up again. And often you will actually see a notation like this one. And again, a notation like the one which we used here, and then the more compact one here, which is actually a tensor product. And the whole many-body space is actually a tensor product of all the single particle Hilbert spaces. And this is just an example of the states which we can set up, and we had just a state which we marked as 0. It could represent a many-body state, or it could just represent a qubit. In our case, the simple case we used was a spinor with length 2. And these are just examples which we also meet when we are going to look at quantum computing towards the end of the semester. So just keep this in mind. And then we defined these projection operators, which also play a very important role. So we have the identity, which in principle sums over an infinity of states. We haven't specified whether these are single particle states or many body states. So we can just leave it, and then from the context, you will be able to tell whether this is a many body state or single particle state. But just think of this as a state of a system. I normally don't use wave functions because the wave function means that you also have time. So I tend to call these states the eigenstates of the time-independent Schrödinger equation. And then you could see now that we have the identity when you then take these two matrices, which are given by the outer products. And these are actually definitions for this specific case of operators, which we are going to introduce pretty soon in this course here. And they are called normally idempotent operators. They are given by the squared operator is equal to the operator itself. And in this computational basis, the thing we saw then is that when we acted with one of these operators on something, so this basis which we have, which we call the computational basis, is not necessarily the solution to a many-body problem, but it is a handy basis which allows us to make an ansatz for the exact function. And since it's an orthonormal basis, we can always expand another function in terms of that. And this function which you see here could now represent the exact solution to the Schrödinger equation. But this is expanded in terms of that basis. In principle, this goes to infinity. Now, if you've chosen a very smart basis, which is close to the exact one, then this sum can be truncated quickly. If you've chosen a basis which does not reflect any of the physics, then you may have to include many, many more terms. And that means that obviously that will slow down your calculations. And this goes back to your question, Daniel, about where do we truncate. So sometimes you're guided by physical intuition. So if you have particles which are trapped in a harmonic oscillator trap, like you would have for quantum dots or Bose-Einstein condensates, and if they interact weakly, then a computational basis based on harmonic oscillator wave functions will often lead to an energy, for instance, or expectation values, which are close to the exact ones. If you have strong interactions, this computational basis may need, in this sum here, many more contributions. And this brings us back to one of the things which we discussed yesterday when we had the computational basis, which in principle is infinite. We would have to make a truncation. So this is a lambda here. And where we truncate and whether we can estimate an error for what is left out depends a little bit on the type of basis set which you have. As I mentioned, for some basis set, you can make a precise mathematical statement of the error of what you left out for some expectation values. So that's normally the typical truncation which we make if we start with a single particle basis. The other thing which we assume then, and we are going to switch a little bit with different types of notations. So this would be a typical one-dimensional object here. We have X, and in our case, this is now a single particle wave function. When I use a lowercase letter for the operators, this means it's a one-body operator. So this acts at a one particle at a time. And if you think of the harmonic oscillator, you know that you have analytical answers for the energy, and you also have analytical answers for the eigenstates. So for the harmonic oscillators, these are given by Hermite polynomials multiplied with an e to the minus x squared term. So there you can actually use the basis set, and the thing which is important for us when you do many-body physics is that you can use this basis set to calculate transition probabilities and matrix elements of operators. And in some cases, like with the harmonic oscillator and a Coulomb potential, you even have analytical expressions for some matrix elements. And that's something which is extremely useful. In some cases, for those of you doing quantum chemistry, where you need, when you solve a many-body problem, you need terabytes or 10 to the 12 or even more matrix elements. You cannot make a table because that would take too much space in memory. But you can calculate the matrix elements on the fly because you have analytical recurrence relations. So this is also a technique which is used in many-body physics. So having such a basis which is meaningful is extremely useful. Then what we did was to define a one-body operator which typically now contained the kinetic energy and an external potential energy. And this, when we say an external potential, this means that we are thinking of a potential which confines the motion of the particle. So in principle, this is something you would apply to the system. So if you have three particles interacting with each other, then it's only kinetic energy and the interaction itself. So in nuclear physics, people often use the harmonic oscillator as a basis because a single particle sees a potential which mimics an harmonic oscillator, but they are not constrained to move in a harmonic oscillator. That's an artificial thing. In nuclear physics, you have only kinetic energy and the interaction between particles. In atomic physics, on the other hand, when you have electrons which are bound, they move when they're bound under the influence of a potential which is set up by the atomic nucleus. So that means the protons. And they would set up a potential which attracts the electrons and forces them to move in specific quantum state or orbits, as they are called. These are things you've seen before, right? And so in atomic physics, you could think of the potential which is set up by the atomic nucleus as this external potential. Then the electrons interact with each other, and that could be represented by this term here. So normally then, and this is the thing we are going to show today through examples, is that if you have a basis, and one single particle basis, which is an eigenbasis of this part of the Hamiltonian, then the basis you construct, the many-body basis, is going to be an eigenbasis also of this many-body part of the Hamiltonian, which includes kinetic energy and the external potential. But it will not be an eigenbasis of the full Hamiltonian. So typically then what you would do is to construct a many-body ansatz based on the single particle computational basis. And in our case, that means that and this is the thing we are going to look at today, is actually that when we have this one body part of the Hamiltonian, the sum over all the one body operators, this actually leads to a problem which has its own eigen states and eigenpairs, as we call them, eigenvectors and eigenenergies. Then the exact state function can then be represented in terms of this expansion here. And normally, if you have a large single particle basis, as we discussed, like here, this can lead to many possible ways to reorganize the particles. So if you're dealing with fermions, which we're going to start with today, what you will see then is that for fermions, the way you can place a given number of fermions in a set of single particle states, like in this case, we actually have n single particle states, and they have a double degeneracy. So that means that we can place a state with spin up and a state with spin down in the same slot here. So if you're thinking of the harmonic oscillator, these could be the first harmonic oscillator state, this could be the next harmonic oscillator state, and so on. So if you have a one-dimensional system, if you are in two-dimension, you have more degrees of freedom for every single harmonic oscillator state which you have, and that will give rise to higher degeneracy. So in one dimension, you can place two particles in every such single particle state. So this is, in case these are spin 1/2 fermions. If they are spin 3/2, you can place 4. If they are spin 5/2, you can place 6, and so on. Does that sound okay? So in this specific case, when you count all the slots you have, what you would end up with then, when you look at this, is actually you would have 2 n slots. So when you're now setting up the basis, you would have to number them. So we could give a new numbering here. So we could start with 1, 2, this could be slot 3, slot 4. And for those of you who are familiar with things like pointers or arrays and things like that, you could now think that this slot 1 points to a set of quantum numbers. So to each one of these, you have quantum numbers like angular momentum, you can have spin, spin projection, the number of nodes of the wave functions, and so on. So if we are insisting on the harmonic oscillator would now have nx equal to 0 here. In this other case, it would have nx equal to 1, and so on. And you know that the harmonic oscillator energy for a given state, nx, is given by h bar omega, and then it has this value of nx plus 1/2. So that's the analytical expression for the single particle energy. So each of the states then has a double degeneracy, but then here you could think of this as a spin up, so you would have an ms equal to plus 1/2, and we normally indicate that with an arrow pointing up, and then we would have an ms equal to minus 1/2, and this is an arrow pointing down. So this specific state which you see here, 1, has these quantum numbers. So if you're in one dimension, you have one spatial quantum number, which is nx. If you're in 2 dimensions, you would have nx and ny. If you're dealing with the Cartesian coordinates, if you go to polar coordinates, you would have n and the projection of the orbital momentum. So depending on the coordinate system, you will have different quantum numbers. But these quantum numbers now, in this case, for the harmonic oscillator, they refer to the nodes which the wave function has. So just to remind you quickly of that. So if you think of the ground state and the probability squared, it could look something like this. This is a ground state. Then you have an excited state, and that could have one node where the wave function goes to 0, or state function goes to 0, and then it has some probability which is pushed out. So when you have nx equals 0, then you have a high probability of being close to 0 in coordinate space. If you have nx equal to 1, then the state gets pushed out from the origin, and so on. So I'm just bringing, because the intuition which we have about the basis sets is actually very important. And that leads to deeper insights about the way we understand the many-body methods, because we build our pictures based on a single particle picture. So that's one of the kind of standard approaches in many-body physics. However, if you have strongly interacting systems, like a Bose condensate of helium-4, where the helium atoms really strongly repel each other when they get closer, a single particle picture is meaningless. So this picture is actually meaningful when a big fraction of the energy is given by the single particle degrees of freedom, like in atomic physics, or in Bose-Einstein condensation, where you have weakly interacting ions. In nuclear physics, you're really on the brink of where this picture is meaningful. In condensed matter physics, you have cases where the interaction is weak, and then the single particle picture you see here is meaningful. But you also have cases where you have strongly interacting fermions, where this kind of picture which we are making breaks down. So remember now that we don't have the exact wave function. And the exact wave function may actually be something totally different from what we're making here. But these ansatses are guided by our intuition and insights about a physical system. So this is a kind of, for those of you doing quantum chemistry, for instance, this is actually the basic ansatz. Start with a single particle basis and then try to build up many body states. Any questions so far? Yeah?
When you constructed the many body wave
function, yeah.
It's a little bit up. Yes, just wondering the D in the summation.
So the D is actually a truncation you have to make.
Yes. Is that related to the number of, like, the other cutoff earlier, the lambda? What's like the difference between the lambda?
No, so this is actually a very good point. And the reason for that, so if you look at that lambda is your cutoff in a single particle basis, which you will make because you cannot deal with an infinite basis. Now, this D, which you see here, that could reflect all the possible ways you can distribute the single particles, right? So if I don't make any further truncation in a single particle basis, which you see here, I have 2n single particle states, I have 4 particles, then D would be equal to this number here. That would be the total number of ways you can rearrange these fermions. However, that case may be a little bit too big. And then people actually play around with making truncations, because this actually explodes. So if you want to diagonalize what's normally called the Hamiltonian matrix, and we are going to see that a little bit later when we look at a method which is called full configuration interaction theory, because then you take into account all the configurations. That's why it's called full configuration. So this is actually what you see here. This image here is actually a configuration. So this is again some of the naming which we are going to use again and again. You can now set up all the configurations which reflect your truncation and single particle basis. Or you can say, in my many body theory, I'm going to leave out some of these configurations. Then you make the second truncation, because you are not able to, for instance, diagonalize. And this is pretty common. And if you diagonalize, if that is your favorite method, then this is normally called not full configuration interaction theory, but just configuration interaction theory. So these are just names, and sometimes these names are confusing, and that's why I want to use some time on this, so that you can see the wood for the trees before we dive into more formalism. Because this is a formalism heavy course, and sometimes you need to have the overarching picture so that you see why this formalism is useful or not. So this is basically what we end up with. So what I'm going to do now is to go through the standard approach of setting up such a fermionic ansatz. And this is given now by a determinant, which is one way to encode the anti-symmetry. That's a compact way of doing that, because you know that when you have a wave function which is anti-symmetric, this means that under the interchange of two particles, it has to change sign. And if you think of a determinant, that is a very efficient way of representing that. So I'm going to change to a new one here, and we are going to call this August. So physics. So this is today's material. So what you saw there is what we went through yesterday. So what we have is a one-body Hamiltonian, H0. And this one-body Hamiltonian now acts on a state. So now I'm going to actually look at the way we represent the state with all the quantum numbers. So this is a state now where I have also included spin. So I'm just going to leave the spin degrees inside this index I. So I've already performed a tensor product here. In many cases, the Hamiltonian which we deal with does not change the degrees of spin. It does not affect spin. If you think of the Coulomb interaction, that does not affect the spin degrees of freedom. The Coulomb interaction is given by 1 over the absolute value of the relative distance. And there's no way you can change the spin. So spin is conserved. So if you go for a state with spin 1, you end up with state with spin 1, because there's no way the Coulomb interaction can change spin. So you have Hamiltonians with spin. Is a Hamiltonian which comes to your mind, which actually changes the value of the spin? There are some famous Hamiltonians, or elements of the Hamiltonian, which you may have seen in different physics courses.
The magnetic field.
The magnetic field. That's a typical example. So if you have particles moving in a magnetic field, you would have to augment this H0 with a magnetic field, and that can flip the spins up and down. That's a typical example. And that's a very actual example, because you often do measurements where you influence the system, or you put on a magnetic field on the system. But let's now assume that, so I'm going to put in the spatial degrees of freedom. And now I'm going to put in, later I'm going to put in a particle label. So it's going to refer to a given particle, but let's just keep it like this. So we are making this assumption. There is an eigenstate, and then we have an eigenvalue. And this is the assumption we make here. Now, what we want now is to set up a many-body Hamiltonian, which is based on this. So this is going to be an operator which goes from the number of particles 1 up to n. So I'm using uppercase n to indicate the number of particles. And this is now an operator which is going to act mainly, in this case, it's going to act on the spatial degrees of freedom. So I'm going to put an I here. Later, and this is an additional notation which we may be using. So I'm going to assume that this H0 is a many-body operator which now acts only on the single particles, the individual single particles. I'm going to sneak in a further notation here, which you will often encounter in textbooks. So let me just set it up here before we move on. So let's just have a small digression, because sometimes I may actually use that, or compact notation, but I'm not going to use that now. So what you will see is something like a compactification of spin and the spatial degrees of freedom in terms of just one variable. So what is common to see, so let me just find my notes here. I just need to find out where I put it. Yeah, here we are. So many people actually look at a variable x, and I'm going to put a vector on top of it, which is now a quantity which contains the spatial degrees of freedom, r, and then spin. This means that your state here will now include both. And what you would see then is that the states, so these are kind of compact notations. So suppose now you have a single particle state where I haven't specified the spatial quantum numbers, which is now given by the spin degrees of freedom. So we have S, it can be spin a half, it can be spin a free half, and so on. So these are fermions now. And this would typically be written in a compact way like R, S, MS. But what you will see is that in many textbooks, especially the one by Nagel and Norland, which we are referring to, you will see this written as X or just X. So sometimes this can be confusing. But that means the following, that when you now are looking at an integral, when you're calculating expectation values, you will typically have an integral which now runs over the spin degrees of freedom. So this will run over, if you now have a S equal to a half, so let's assume that, just to give you an example. This will run over S, ms equal to plus minus a half. If these are bosons, they have integer values for the spins, and you will also have a loop over the integer values for the spins. So you can replace this you can go from fermions to bosons without any problems. And then what you will see then is that this will be written like a D, and now I'm just putting an R here. So this can be 1 dimension, 2 dimensions, 3 dimensions, or higher dimensional quantity. So this is a kind of notation which we will encounter. This means that when we look at the standard quantity which we have when we are looking at the normalization of the states, this is going to be given by a Kronecker delta for ms. So we have a state x and a state x prime, and it's going to have delta, and then I'm going to put a d here for the dimensionality of the system, and then we're going to have an r minus an r prime here. So that means that when I write now the norm here between two states, or the inner product, this would actually be given like something like this. So these are more compact notations. But now what we are going to do is actually go back, and hopefully there won't be any kind of misunderstandings, but we are going to label the states, the single particle states now, SP states. I'm going to label them like this, phi of I, and then I'm going to have explicitly the spatial degrees of freedom. So this I can contain single particle quantum numbers like the spatial degrees of freedom, but it can also contain spin. So what I've done here, I've already computed a tensor product with the spin degrees of freedom. And then I'm going to put a J. So this is going to refer to particle J. Particle J with the quantum numbers I. So if we now look at fermions, and let's now suppose we take two fermions. So, and we look at the case with n equal to 2. The way we would represent the many-body state, so we will have an ansatz for a many-body state, which is now built upon the single particle states. So I'm going to call this for phi, and this is going now to depend on the positions of particle, since we have two particles, particles 1 and particle 2. And in order to normalize it properly, we need to have 2 factorial, which is actually 2 here. And this can be written out as a determinant. And this determinant, the way I'm going to set it up is in terms of the specific quantum numbers which they can occupy as rows, and the particles as columns. Okay? So I'm going to have a specific quantum number the system can be in, and let's just call this a quantum number alpha. And then I have particle 1 here. Now, due to the uncertainty principle, and the anti-symmetry, this being indistinguishable particles and so on, we would actually have, we don't know whether particle 1 is in state alpha or in state beta. And this is again, so we have the quantum numbers as rows in this determinant matrix. And then we have an R2 here. So this would be the ansatz for a two-particle system, where we now have chosen states alpha and beta without specifying them. I guess you've seen something like this in different courses before, right? So when you took Physics 3.110, you probably, or quantum mechanics, you probably looked at systems of spins. And then you have defined a wave function which is antisymmetric. And you see now that if you interchange, you see from this function here, that if we interchange now particles 1 and 2, we see that this is equal. And you know that when you switch two columns in a determinant, that gives rise to a minus sign. Any questions? Feel free, guys, to ask questions here. So I'm just putting up definitions here. Now, there's one thing I just wanted to quickly remind you, because we are also going to introduce a more compact notation a little bit later. So I'm just quickly going to switch back to the slides which we have. So if you scroll down a little bit, so this I'm just going to set this up. This will be a typical example of a many-particle Slater determinant. Now, let me just remind you of some properties of determinants which will be useful for the things we are going to do now. So if you look at a determinant, that's just a general definition, which you see here. You can actually rewrite that one. So this is a matrix, and I write it det. And the kind of notation you will often see is that you have this kind of vertical bars. That's one way of writing it, or you write det A. If you look at this notation here, and this is something which is important because we are going to introduce this permutation operator. So this actually acts on pairs of particles, and it just interchanges them. So it permutes particle I and particle J. So this equation which you see here can actually be rewritten in a more compact form like this, in order to convince you about that specific formula, because we're going to use that one. You can see that if you do look at a 2x2 determinant. If you look at that one, you have this case with 0 permutations. That's the first part in this sum here. And then since you have only 2, you can only permute once, right? So this is a number of permutations you can make of pairs. And in this case, when you permute 1 and 2, you get a minus sign. And if you look at the expression you have here, this is just the expression for the determinant, right? Nothing but that. So what you're doing then, we have interchanged the column indices 1 and 2. And now there's something I want to emphasize before we take a break. This it relies on you having chosen an ordering. So this becomes important when we are looking at the way we organize the determinants or the wave functions. So we have to choose an ordering. That ordering of the single particle states can be random, but it's common to order it according to the single particle energies. So like in the figure which we saw previously, if you order that according to the single particle energies, you could start with the lowest state as state 1, and then you move on. But you need a specific ordering, because that tells you what has been changed. So you have a basic ordering, and we are coming back to that in the next lecture, and we are going to see the importance of that. So if you look at the determinant here, we have chosen a natural ordering as 1, 1 and 2, 2 here along the diagonal, but you could have chosen it differently, right? And that means that the permutations you see are with respect to the way you have organized your diagonal. So this is just a quick reminder of some properties of determinants, because we are going to use this more compact notation when we now are going to calculate expectation values of the energies with these operators. So I'm going to put the recording on pause now, and we just take a small break, just stretch legs, just do our holding. So what we have now is a featured determinant, which we're actually going to use when we now are going to calculate the expectation value of the one-body part of the operator on a two-particle state. And then what we are going to show is that this is going to be the sum of the single particle energies. So we have for a many-particle state, we are going to have an analytical expression for the non-interacting part. So parts of the Hamiltonian will have these states, which we are going to construct now, which we call the computational basis, will have these as eigenstates. So let's switch back to the whiteboard here and just do this kind of a little bit boring calculation and just go through things in the kind of what people call the first quantization representation. So what we're going to do now is to take this state, and I'm going to rewrite this in a compact way. So this phi, and just skip the different coordinates. I'm just going to call this for phi. And what we could also do now, we could assume that we have such a basis. So we have a single particle basis. It may have some degeneracies or not, but let's just call this a slot 1. And this is a slot 2. This is a slot 3, and so on. And this goes up to a state lambda. And we are now thinking of these slots as slots which now just contain one fermion. It could be an electron, it could be whatever kind of fermions you're looking at. So you could think of now as this is our system. And when we now look at the energies here, when we have this epsilon 0, and then we are going to act on this with a state 1, this is going to be given by an epsilon 1 times the state here. And then this is just going to go on. We have the state I. There's going to be a single particle energy which has an analytical expression and is well determined. So that means that when we now set up the wave function, what we need to calculate is actually an integral. And let's just go through the calculations now. And then we are going to generalize this. So the first step now, we do this in a brute force way. This serves also to motivate second quantization, which is going to give us a much more compact formalism, which is going to simplify the calculations of these kinds of expectation values. But first we have to do this kind of a little bit boring exercise. So what we are going to calculate now is actually this quantity here. And we are going to only look at the expectation value, and I'm going to call phi 0, and I'm going to define what I mean by phi 0. So phi 0 is the lowest lying state I can make, because I'm going to organize these energies so that epsilon 1 is smaller than epsilon 2, and so on. So there is a hierarchy. And this is an ordering which I have chosen. And this is going to define later a basic ordering, which will then decide how you set up the determinant. And when you're going to look at different expectation values, this basic ordering is going to be important when it comes to the kind of signs we get if we interchange particles. And we always want to reorganize everything in terms of this basic ordering. So that means that the state which we are going to have now, this phi 0, is now going, or not phi 0, but let me write it like this. This is going to be the tensor product of state 1 and 2. And this tensor product now is going to be given by a determinant. So when we write it out in terms of all the Slater determinants, we are going to have a factor of 1 over square root of 2. So it's a 1 over square root of 2 times 1 over square root of 2 here. And then we have an integral, and this integral is over dr1, the first particle, and then we have a dr2 here. And now we need to look at the bra side of the expectation value, and that is going to contain this state 1, and then I have an r1, complex conjugate, obviously. And then I have a psi2, and this is an R2 here, complex conjugate. And this has a minus because now you're calculating the determinant, right? So if you go back here and you look at the determinant, I now put labels 1 and 2 here because they refer to the two lowest lying states. And we are going to use that as an ansatz where we assume now that the ground state of the system, which is the state with the lowest lying energy, or the fundamental state as we also call it, is going to be the state which is dominated by these two single particle degrees of freedom. Okay, so then we are going to have a psi1, but now we have made the flip or the permutation between particle 1 and 2. And then we have a psi2 here, and then we have an R1 here, like this. So this is just us spelling out the Slater determinant in the gritty-nitty details. Then this is multiplied with, and then we have an H0 of R1. That's the operator that contains kinetic energy and the external potential energy. So I'm just writing out explicitly the sum. So I promised you this is not going to be the most exciting thing we do today, but it's useful to have seen this at the 2-particle level. If I were to do 3 particles, I would have 6 possible permutations, and it wouldn't be so fun. And that's why we introduce second quantization, which gives us a much more compact way of calculating these expectation values. And then I have to multiply this with the ket side. So I put outside this factor of this normalization factor. So I have a 1 of R1 here, no complex conjugation, of R2 here, minus psi1 of R2. I've interchanged the columns, and psi2 of R1, like this. So what you see now is that you're going to have 1, 2, and then 2, and then you're going to have something like, for every HR10, you're going to have something like 2 terms here. So let's now look at the multiplication. So we have a 1 over half, 1 half. And now we have to remember that H0R1 acts only on particle 1. So that means that when we are looking at the integrals here, we would have now one integral where we have dr2 here. And then we have, so if we take this term and multiply with this term and that term, so that's the first term we're looking at, then what we would have is a psi2 of R2 complex conjugate with psi2 of R2. And then we have a d of R1. And then in what we have is a psi1 complex conjugate of R1. And now I have H0. And I'm skipping the R1 here. And this is acting on R1 and psi1, phi 1. So if you now look at this integral, so before we start writing the other ones, because as soon as you look at this one, you are going to see the pattern immediately. So if you look at this integral, the 1 over dr2, we have assumed that the wave functions form an orthonormal basis of the state functions. So if you look at the first integral, the 1 over dr2 here, what should that one be like? What should that one give us? Yeah? Yeah, the 1, exactly. This is normalized, right? So if we now mark it here, so this is equal to 1. If we look at the second integral, so we have assumed that these are eigenstates of the operator H0. So what would the second integral give us here? Yeah?
Epsilon 1.
Epsilon 1, exactly. So this second integral, so let's do that, and down here, this is actually going to give us just epsilon 1. So let's do the boring exercise and just go through some of the next terms, because you will quickly see the way things are going to evolve here. So let's now take this term here, which we have, and then we still multiply with this term, but now we multiply with this one. So let's look at what we get here. So we get a minus, obviously, and then we have an integral over dr2 and we still have this phi 2 of R2 here, but now I have this quantity here, which I have to plug in. Phi 1 of R2 here. And then there's going to be an integral over dr1. But before we put up that one, I'm just going to put dots here. Do we actually need to put it up? No, because these form an orthonormal basis. So this is actually equal to 0. So what you see now is that the cases here where we have a state here which has not been permuted, and multiply with the one which has permuted, that gives us zeros. It means also that if I now take this one and multiply it with that one, and then together with that one, what should that give us? If you look back at this integral, so if you now take this term here, multiplied with this term, R2, and then again multiplied with that term,
you get epsilon 2.
Epsilon 2, yes, exactly, because then you would have H0, R2, acting on this state, and then since the states are normalized or orthonormal, this one with that one will just give us 1, like this integral here. So we are going to get a plus 1/2 when we do that. Now, suppose now we are still looking at this term here. We multiply it with this one, but now we multiply it with that one. What should that give us? That gives us 0. Excellent. So we get a plus 0. And now we repeat everything, because now we go to this term here, right? And now I multiply this term with that term, and then with this term. So what would that give us? So we take this term, we've done the first one, multiply with this, and then multiply with that. You have to be a little bit careful, because now if you look at this term here and this one, that is going to have HR1, which will pick this term, and then it will pick that term. And then you will be left with an integral. So the next integral would have it's actually a minus. So let me correct that. So the next integral is a minus, and then I have a dr2 here, and then we are going to have a minus phi 1 r2. But then I'm multiplying with the first term here, which is this term here. So it's going to have it's going to have a phi 2 r2 here. And then I have the 1 over dr1 here. And you see this is also equal to 0. So many of these terms disappear. All the terms which have a non-unpermuted term, which means the one which follows the normal ordering, which we have, it has a diagonal matrix element, and multiplies it with a permuted one. It means that you will have different states which connect, and then the orthonormality kicks in, and it becomes 0. So it's normally, actually these kind of terms have a specific name. So this term which you see here, this one, is normally called the direct term. And it follows the way you have ordered the diagonals in the determinant matrix, which again follows the ordering you have chosen here. But then when you permute or you interchange two rows, all the terms where you have a one body operator which act on that, they give 0. So now so we had the minus term here, and if we now multiply it with this one, and still R1. So take a look at this one, minus, minus obviously plus, and then I have R1 here. What should that give us? It's actually epsilon. It's going to give us, because it's, if you look at this state here, R1 is in state 2. So it's going to give you epsilon 2. So the next one gives plus epsilon 2. And then, when you then continue, so what we did now was this one with this one and that one. Now we could take this one and multiply with this and with that. And what would that give us when we look at the eigenstates and the orthonormality? So you see you have a state which has been permuted and one which has not been permuted. So that should give us 0, right? When we have a one-body operator. So we get a plus 0. And then I guess you can guess what the final one should be. So if I now take this specific term which you see here, this one, and I multiply with that one, and multiply with this one, what should that give us? Epsilon 1, excellent. So if I sum up now, epsilon 1, so what we get, we have two terms, so we have epsilon 1 plus epsilon 2. So in general, what we are going to have, if now phi is a many-body state, so in general, if phi is now a state which contains R1, R2, up to R of n, then this expectation value of this state, phi 0, and we call it phi 0, for instance, just one of them, of H0, the general expression is actually going to be given by the sum of the single particle states, I equal single particle state energies of epsilon of I. And I'm going to use a kind of notation for that. So I'm going to call this epsilon 0. This should be an uppercase epsilon. And that refers, in this case, to the state which you have 0 here. If you have another state where you fill in different single particle states here, then it will have another label. Because you can distribute these particles as you want. But each of these states which you have, these Slater determinants in our case, as they're called, they are eigenstates of H0 by construction. So there's a theorem I'm going to state without showing the proof. So if you have an orthonormal single particle basis, you can build automatically an orthonormal many particle basis, whether this is a symmetric wave function or an anti-symmetric wave function. So I'm not going to show the proof for that, but you can actually prove that. So choosing an orthonormal single particle basis allows you to construct an orthonormal many particle basis, and we will call both of these for computational basis. So we have a computational single particle basis, but we also have a computational many particle basis. So computational because we build the true wave function based on this ansatz. So if you have a non-interacting system, then this is the exact solution. Okay, so I'm going to introduce another notation here. So when you look at this term here, so this is something we're going to use quite often. This is going to be given by an integral where I now have a d of r. We don't need to specify r, whether this is particle 1 or whatever. And then I have a state phi of I of r multiplied with this operator H0, which is a function of r, multiplied with the state phi of r. So we have made an assumption that these states are now eigenstates of that basis. Later, when we are dealing with something which is called Hartree-Fock theory, then these states will be the eigenstates of another one-body Hamiltonian, but which includes the effects from other particles in terms of you solving coupled single particle equations. So you can always redefine your single particle basis. So some of you may have taken a course on DFT, density functional theory. Has any one of you done that? Okay, then we can just wait a little bit with that. So this is a notation we are going to use, but you will also see this in the following way, H0 of I. This is also another way of representing it. And sometimes we just skip the hats because it's implicit that this is just an operator. So you will also see this as I of H0 of I. Now, since we now got pretty ambitious, and this was actually not that difficult to calculate, let's take a look at the interaction. So we have assumed that there is another part of the Hamiltonian which describes the interaction between the particles. And we have assumed that this is given by the sum. It's a double sum over all the particles, but obviously you don't want to calculate the same energy twice. So you can always restrict the sum. And also there are some specific symmetries of this interaction where we then define this as an Rij. And Rij here is actually the difference, the relative distance between the two particles in positions I and position j. And this Rij, is then a notation which we are going to use for the absolute value of this quantity here, which is the same as the square root of xi minus xj squared. And depending on how many dimensions we have, we can just move on with y and z and so on. So I just put dots here because that depends on the dimensionality we have. So if we're just in 2 dimensions, it's x and y, and so on. So this is a kind of notation which we are going to use throughout the course when we introduce an interaction part of the Hamiltonian. And a typical example could be the Coulomb potential, which we often will just call the Coulomb interaction, because this is the piece which lets the particles interact. Okay, so now what we're going to do is to take the same state, phi 0, which we defined for 2 particles, and then we're going to calculate this expectation value here of phi 0. And we're going to do it for 2 particles because it also serves the purpose of bringing in another definition of so-called matrix elements. So these are actually transition probabilities where you go from a state I and you operate with that one with the operator H0 and you end in a state I. So these quantities here, just to remind you, since this is an orthonormal basis, this is actually given by delta ij epsilon I. So in case they're different, then obviously this is 0. This is a choice. It doesn't need to be diagonal. You can actually have a single particle basis which may not be diagonal for H0, but it could be diagonal for a Hartree-Fock single particle operator. So you have an H0 which is determined in terms of kinetic energy and the external one-body energy. But if you do a Hartree-Fock calculation, you actually add a modified single particle potential, which reflects the medium. And then this H0, which we defined, this relation here, may no longer lead to eigenstates of that specific H0. So these are choices which we are going to make throughout the semester, depending on the type of systems we are studying. Okay, so in this case, we now have again the factor 1 over square root of 2, 1 over square root of 2, and then we have the integrals. And now I'm looking at particle 1 and particle 2 here, and we are taking the complex conjugate part of the wave function. So we have an R1 complex conjugate here, particle 2 here, complex conjugate, minus, and then I have a phi 1 interchange of the columns. This is now multiplied with this operator, which is R1, 2. And this is multiplied with phi 1, R1, phi 2, R2, minus phi 1, R2, and phi 2, R1. Okay, let me now just write out the different terms. So let's take the terms which are going to give us a positive sign. So I'm going to take this one multiplied with this and multiplied with that. Then I'm going to take this one multiplied with this and the interaction. So I take first the terms which give us a positive sign, okay? So what I'm going to get then is a plus 1/2, and then I'm putting dr1, dr2, and now I'm going to have phi1, r1, or v, r1, 2, and then I have a phi1 and phi2, r2 here, and then I have plus, and I have a phi1 of r2, phi2 of r1, of v r1, 2, phi1 of r2, phi2 of r1, and then end of the parenthesis. Now if you look at these terms, these two terms, and you go back to the potential which we have defined, or the interaction which we have defined, what happens with this term here when I interchange I and j? Nothing. So it means that if I now interchange I and j, or 1 and 2 in this case, I should get the same result. So if I look at this final expression, remember now that these are just dummy variables, right? So I can always relabel them. So if I, in the second term, interchange R1 with R2, what do I get then?
Zero.
No, it's the same as the first term. If I just replace, so I do R1 here, R2 here, R1 here, because these are dummy variables, right? And this element here multiplied with this one, I can always relabel R1 and R2 in R5 and R6. So they're just dummy variables. I can always relabel them, right? So if I do that, you see that you have two equal terms. This is actually very important properties. And there are, till now, for many of the important fundamental physical interactions, there are no evidences that this kind of symmetry, which leads to translational symmetry actually, is broken. So people have actually tried to search for the breaking of some of the symmetries for the fundamental interactions, and still there are no experimental signs that we cannot do what is here. So this ansatz that your interaction depends only on the absolute value of the relative distance, there are no experimental indications that this breaks, presently. So that's a very important property. Actually, people have also mounted experiments to see if there are ways to break the Pauli principle experimentally. So within present-day experiments, there is no sign that the Pauli principle does not hold. So the Pauli principle is the one which states that a many-body wave function for fermions should be anti-symmetric with respect to the interchange of two particles. So experimentally, and some of these experiments have been pretty ingenious, there is no sign of that. So we can assume then that what we did here, since this potential depends only on the relative distance and the absolute value of it, then just by interchanging the variables, we have two equal terms. Now, if we now look at the second one, we will get minus a half, and then we would have a dr1, so I'm just, and dr2 here, and then we just repeat the same exercise, and we would have a phi1 of r2 here, and then we have a phi1 of r1, and this is multiplied with a v r1, 2, and multiplied with a phi1, and then I would have an r1 and a phi2 with r2, and then I would have a new term here, which goes like minus or rather plus, since I put the minus sign outside, I would have a phi 1, R1, phi 2, R2 here, and a V of R1, 2, multiplied with a phi 1 of R2 and a phi 2 of R1. And here as well, we can do the same thing, but interchanging R1 and R2 in the second term, and then you will see that these terms are also equal. So that leads us to the following. It leads us to a result where we have dr1. So now we cannot separate this in two distinct integrals for R1 and R2, because now we have an interaction which connects the particles, which means that we cannot have a product of an integral with R1 and an integral with R2. So we would have the first term here, which simply runs like this, of R1, phi 2 of R2 here, multiplied with the interaction, R1, 2, and then this is multiplied with phi 1 of R1 and phi 2 of R2 here. This term has a name, and this is actually called a direct term. And we are going to label this in the following way. So this is going to be a 1, 2 of V of 1, 2. So this is the compact notation we will use for this transition probability, or we are going to call these matrix elements. And then we have the second term, which is now given by dr1, dr2 here, of phi 1 of R2, phi 2 here of R1, multiplied with V R1, 2, and this is again multiplied with R1 of phi 2 of R2 here. And this is called the exchange term because we have exchanged the two particles. And this is due to the Pauli principle. So the Pauli principle states simply that the wave function has to be antisymmetric. When we use a single particle basis like now, the consequence is that no orbit can be occupied by more, or single particle state can be occupied by more than one particle. If you have bosons, on the other hand, you can actually fill it in with as many bosons as you want. So this is the exchange term, or the Pauli exchange term, as many people call it. And then what we have here is that this is going to be rewritten because now we have interchanged R1 and 2, so this will be written as 2, 1 of the 1, 2 here. So in total then, we have a matrix element which is given by 1, 2 of V, 1, 2 minus 2, 1 of V, 1, 2 here. Now we can generalize this to other states. So the general situation which we're going to have is something like this, P of Q of V, and then we have PQ, so this is a direct term, minus, so now we have replaced 1 and 2 with just a random state, and this will be given by QP of V of PQ. Now it's common in the literature to merge this together because when you're running the calculations, it's handy to actually compute both of them and make a table. So what you will see is often something like this. So PQ of V, PQ, anti-symmetrized. So anti-symmetrized because the exchange term follows from the anti-symmetry of your state function. And what you would then tabulate would be a set of matrix elements which are now simply given by these anti-symmetrized matrix elements, but where you have actually calculated these integrals. So these integrals need to be calculated. You can easily see here that if you have many single particle states, this quickly blows up. So if you have 100 single particle states and you don't make any kind of smart reordering, so you could think of this, you have 100 here, you have 100 squared, That's the number of states you would get. And you would have 100 squared here. So 10 to the 4 times 10 to the 4. So you would have 10 to the 8 such elements. And that can quickly grow. So in many implementations in, let's say, quantum chemistry, many people actually calculate or have recipes to calculate these matrix elements on the fly instead of storing them. So as soon as you get into terabytes, you may actually think of doing something like that. If you're below that, number of matrix elements, which again depend on the basis set you've chosen, you can actually store them in a calculation and just look up a table. Any questions so far? So I'm just giving you all these kind of definitions because these are kind of definitions and notations which we are going to need. Yeah?
Did you forget the complex conjugation in the integral?
Thanks. Okay, so what we're going to do next now is to generalize this to a function which has more than 2 particles. So I want to do this now to baby step you so you see the basic machinery. But now we're going to go to a many particle state, and you can still do this type of calculations, but it becomes a little bit more cumbersome. So I'm using this in a way to motivate for second quantization as well, because that's going to give us a much more compact way of calculating these kinds of expectation values. So let's look at how we can do this for a many particle state. So what we are going to do now is to look at the Slater determinant, so which we defined. So let's now look at an n-body Slater determinant. So it's called, these determinants are called Slater determinants because Slater was the first person who actually introduced this. Actually, in the beginning, this is actually quite fun. So Slater Jr. was actually the one who did the physics, and Slater Sr. was actually the father, who was an engineer who was good at computations. And in the first time when they run the calculations, they actually skipped the Pauli principle because they didn't know about the Pauli principle. So when they calculated matrix elements, they actually had a wave function which wasn't properly symmetric or anti-symmetric. And they only dealt with the direct term. And they developed what were called the Hartree types of equations. Then with the Pauli principle, you could actually include the exchange term. And when you were looking at simplifications like what is called Hartree-Fock theory, and Fock was a Russian mathematical physicist, then you had to introduce the exchange term. And then Slater actually came up with the determinant representation, and that's why it's called a Slater determinant. Okay, so the n-body SD, this is a kind of acronym which I'm going to use for Slater determinants. If we look at that one, we can obviously write it out in the following way. So if we now look at the state phi, and we can specify whether this is the ground state or not. And this state phi will now contain a given number of particles up to R of n. And we are going to have a set of quantum numbers or slots which the states are going to occupy. And we are going to look at the ground state. There's an ansatz, and there will be slots, alpha 0, alpha 1. So these are the quantum numbers up to, or rather let's start with 1 here, 2, and up to alpha n. So these are the quantum numbers, the specific quantum numbers. And in this case, what we would have is something like this, 1 over n factorial, and then we're going to stop here and with a general expression for this. So this would be given by alpha 1 of R1. I would have an alpha 2 here of R1, and this goes all the way down to alpha of n of R1. So that's the first particle. We don't know in which state it is. That is because these are indistinguishable and identical particles. And then this goes on all the way to R of n. And it goes down to alpha of n of R of n. Now, if you have some spare time problems in the weekend, you could try to repeat this exercise with 2 particles and just do a 3-particle Slater determinant. And then you will have 6 possible permutations. And then you will get 6 times the interactions times 6, so you will have 36 elements. So we need to find ways to compactify these calculations. Now, what comes to our rescue then is this more compact way of writing it. So we are going to write it as 1 over n factorial. And then we are going to have the sum over permutations, this p. And this is given by -1, depending on the number of permutations we've done. Just going back to that expression which we looked at for the determinant, the 2 by 2 determinant, for instance. And then we're going to have a permutation, so this acts on pairs. And this is going to be multiplied with the ordering which we have chosen, alpha 1, R1. So the ordering which we have chosen for the single particle states is now going to play a role when we start looking at permutation. So we are going to permute with respect to a given ordering of the single particle states. So that means that we have a product now. So if I take only the product, I won't respect the symmetry requirements, but this operator P does the job for us. Now you can rewrite this, and this is the last thing we do today, in terms of n factorial, a new operator, which I'm going to call the Anti-Symmetrization Operator, multiplied with a function which is normally called the Hartree function. And the Hartree function was actually what Hartree did when they set up the first equations. They actually took that, they didn't know about the symmetries, so they just had a product of the single particle wave functions. So this A is a permutation operator or anti-symmetrization operator, and it's given by n factorial, and it has simply the sum over all the possible permutations. So this acts on pairs. So the operator here only permutes 2 and 2 particles at a time. And it loops over all the possible permutations you have. So if you have 2 particles, you can only make 1 permutation, right? Sounds obvious, right? And then this phi is called the Hartree function, and that's just a product of the single particle wave functions. R1, R2, and this follows the ordering you have done. So when you want to calculate something, you will always now refer to this ordering. So knowing which permutation you made becomes important. So this will be an alpha n of Rn.
I can see what would actually be the difference in the end if we selected another ordering from the start.
Oh no, you just have to keep that one, because when you use that basic ordering, that means that when you make permutations, your matrix elements are calculated according to a basic ordering.
All right, so just be consistent.
Just to be consistent. Because if you change, if you don't go back to the, if I now permute particles, and then I want to calculate matrix elements for the many-body system, they're calculated according, they're set up as a table to save space. As simple as that.
Or else you would be counting permutations wrongly.
Yeah, and that would just blow up your dimensionality. So we will see that next time. So we are going to stop here, and I'm going to stop the recording. And next week, let me just end here. Let me stop the recording.